All right, so this begins our unit on the Earth and life through time. And it's one of my favorite units because it looks at the Earth and life through time and how they have changed together and influenced each other's development. So, geology is the study of the Earth, but the study of life on the Earth and how ancient life changed over time is the study of paleontology, which is a branch of biology. So remember, biology is a huge umbrella, and a lot of other fields fall under that umbrella of biology, and paleontology is one of those. So if you're interested in digging up fossils and learning about once living organisms and studying evolution, paleontology is the field for you. So paleontologists and what they discover depends primarily on fossils. And there are different types of fossils. The main types are molds, which are impressions. So, for example, you may find a fossil that is the impression of a leaf. Casts, which are molds that have been filled in. Traces. So you may see even like a trail where a worm crawled through the mud can be fossilized. Nests, burrows, footprints, like they found all kinds of dinosaur footprints. That's partly how we know that dinosaurs, some certain dinosaurs were bipedal, walking on two legs. And I just read an article recently where they found a fossilized turtle that looks like it was crushed by a sauropod dinosaur, one of those huge plant-eating dinosaurs, because they found it where there were tracks of sauropods. True form fossils are the actual animal or part, and the best example of that would be like a woolly mammoth that has been frozen in the permafrost up in the tundra. So, woolly mammoths went extinct about 10,000 years ago, but they find them frozen in the permafrost, and it's almost like putting meat in your freezer. It preserves it, and even the soft tissues are preserved, because normally it's only the hard tissues that are fossilized. Some of what can... and another true form example would be this scorpion in amber. Amber it's tree sap that encases an animal that might be on the bark of the tree, so the animal will be on the bark and a big glob of sap will engulf it and encase it. And that sap then will turn into amber. It fossilizes into amber. And that's the basis for the movie Jurassic Park, actually. They found insects in amber, and they got the blood, dinosaur blood, supposedly, from the mosquitoes in the amber, and used the DNA in that blood to resurrect dinosaurs. An interesting idea, but we haven't been able to figure out how to do it yet. So what can we learn from fossils? The morphology, and there's a vocabulary term you really need to know. Morph, if you are familiar with that word morph, maybe from a video game or something, morph just refers to the shape or the form of something. So morphology, the shape or form, the time that organism or species lived, the phylogeny, in other words, the evolutionary relationships with other organisms by comparing the morphology of one species to the morphology of another species. We've been able to figure out how species are related to each other even though they're no longer living. Their habitat, depending on the surrounding fossils, the plants that are fossilized around the fossil and other things that are available and fossilized, we can determine to some extent the habitat, even pollen, microscopic fossils that are fossilized in the rock. We can infer behavior. So, for example, if we find an animal near or on a nest that has eggs, fossilized eggs, a fossilized nest with fossilized eggs, we might infer that that's the parent of those eggs, and it's actually sitting on those eggs or incubating those eggs or protecting those eggs until they hatch, just like birds. And there have been dinosaurs that have been found in that situation, fossilized. DNA sequence. Some of the more recent fossils, not the dinosaurs, we can't really get DNA information from because they died too long ago, at least 65 million years ago. But more recent fossils, we can actually extract DNA. So, for example, like from woolly mammoths, and it's been suggested we could use that DNA to resurrect woolly mammoths if we wanted to. But again, that technology hasn't really been developed fully yet. So, will we ever have a complete fossil record? And by the way, all the fossils that we found is known as the fossil record. It won't be complete because there are too many organisms that have lived. We don't even know how many species are on the planet right now, let alone all the species that have ever lived. Not all of the species that have ever lived fossilized. Some of them were soft, don't have hard parts, therefore they didn't fossilize. And we can't find or unearth every single fossil that there is on the planet, so the fossil record will never be complete. Just a couple of vocabulary terms here, and I'm sure you already know what extinct means, but it means the species is no longer living on the earth, right? Extinct. Now, a term that is the opposite of extinct you may not be as familiar with. It is extant. Extant refers to a species that is currently living on the earth. So these are the species that we now have living on the planet. The opposite of extinct. So they are not yet extinct, and hopefully they never will be extinct. Greater than 99% of all species that have ever lived are now extinct. That means that less than 1% of the species that have ever lived are now extant, are now living on the earth. That's why we will never have a full and complete fossil record, again, because there are so many species that have lived on this planet over its 4 to 5 billion year age. You probably already have an understanding of how fossils will form. This is just one example of a fish fossilizing. The most common fossils are molds and casts. They're most commonly found in sedimentary rock, and that's the example that we see here. And sedimentary rock most often forms in aquatic environments, water, because particles will wash into that aquatic environment, a stream or a lake or a pond, and that sediment will then settle to the bottom and build up over time, layer after layer after layer. And that eventually forms sedimentary rock. After it builds up layer after layer, that applies pressure, and then heat will turn it into sedimentary rock. So the fossilization process begins when an animal carcass, a dead animal, is buried by sediment before it is eaten or completely decomposes. That's an important part there. It has to be buried, completely buried, before it completely decomposes. And then over time, the surrounding minerals replace the hard parts, and under heat and pressure become rock. Strata refers to the layers. So like these different colored layers that we see in the diagram, they're layers of sediment that have turned into sedimentary rock. And those layers of sedimentary rock are known as strata. The deeper the stratum, and so that's the form of the word, singular form of the word stratum. One layer is a stratum. So the deeper the stratum, the longer ago it was formed. Not every organism that dies is fossilized, as I mentioned on the previous slide. That's why we'll never have a complete fossil record. Conditions favoring fossilization are being buried shortly following death in cold and or anaerobic conditions. Anaerobic, vocabulary term, that means without oxygen, because decomposition depends on bacteria that need oxygen, that use oxygen. So if something gets buried and the oxygen and it's sealed off from oxygen by being buried, then decomposing bacteria can't decompose it, and it will fossilize. It's more likely to fossilize. The parts of the organism that often preserves are hard parts, like skeletons and teeth and shells. Soft tissues are sometimes preserved under extreme cold, like permafrost, like the woolly mammoth that I suggested or mentioned on the previous slide, or hypoxia, which is another word that means without oxygen. So in extreme conditions where there is no oxygen for decomposition to take place. For example, amber, the tree sap that engulfs an animal and encases that animal. It's just like putting the animal into a Ziploc bag and no air can get to it, no oxygen can get to it. It's a hypoxic environment. And also DNA can be preserved. Again, under extreme cold conditions. So like I mentioned on the previous slide, woolly mammoths, we can get DNA from woolly mammoths, complete DNA, and we may be able to use that to resurrect them, as I mentioned here. But it at least can be used to determine phylogeny, in other words, evolutionary relationships with other species. For example, like with the woolly mammoth's relationship with elephants. We can actually use the DNA to see how that relationship, what that relationship is. And we can do the same with our own relatives, evolutionary relatives. So how do we know the age of a fossil? Well, these very special fossils known as index fossils are one way, and that's an example of relative dating. So in other words, relative means in comparison to something else. So it's a method of determining the age of a fossil by comparing its placement with that of fossils in the same or other layers of rock. So if we find a fossil near another fossil, if we find a fossil and we don't know its age, but we find it near another fossil that we do know its age, then we can infer that they lived around the same time, close to the same time. And that's an example of relative dating. And again, it's done by either knowing the age of the strata. So, for example, these layers of rock here, we know all over the Earth that certain layers were laid down at a certain time. So if we find a fossil in that layer, we can infer that that organism lived during that time that the stratum was laid down. Again, index fossils are very useful because there are certain species that we know when they lived. They lived for a relatively short period of time, so it narrows down the time that an organism that is found with that index fossil lived. And they were very widespread. So those are basically the characteristics of a good index fossil. So again, they were very numerous, widespread, existed for a relatively short time. So again, if you find a fossil of something and you don't know its age, and you find index fossils all around it, in the same stratum all around it, and you know the age of the index fossil, then you can infer that the age of the specimen that you found that you don't know the age of is very close to that of the index fossil. So index fossils include things that fossilize very well. That's another characteristic, actually, that should be in this list. So they're numerous, widespread, existed for a relatively short time, and also have hard parts that fossilize really well. So, for example, mollusks in general fossilize really well because they have shells. Foraminiferans fossilize really well. You probably have never heard of foraminiferans, but they're microscopic amoebas that form calcium carbonate shells around themselves, and therefore they fossilize well. But they're microscopic. You need a microscope basically to see them in the rocks, but they are very good index fossils. They have been used very extensively as index fossils. And then trilobites you may also be familiar with because they're so famous. They're so numerous. But they fossilize really well because they have an exoskeleton. They're arthropods, so they have an exoskeleton. And that means they fossilize really well. So they make really good, and there have been many species over time. So they make really good index fossils. So relative dating is not very exact, right? Hope you probably got that impression from the previous slide. But we also have absolute dating. And absolute dating is the determination of the actual age of a rock or fossil, the actual age using a technique like radiometric dating, what's known as radiometric dating, which uses a radioactive isotope, which is an atom that has a different number of neutrons. And we haven't covered chemistry yet, the chemistry of life, that's one of our units. But you'll learn that an isotope and this is something you need to know now, an isotope is an atom that has a different number of neutrons, and sometimes that makes that atom unstable so that it's radioactive, and it throws off particles, and it actually turns from one element into another element. So in this example, we're looking at potassium-40, which is a radioactive isotope, and it emits radiation, and in doing so, it turns into argon. It turns from potassium-40 into argon, which is a different element. And it takes a long time for that to happen, for any sample anyway, for the whole sample to turn into argon. And we can use that, the amount of time, the period of time that it takes to determine the age of a rock that contains potassium-40. And basically all rocks contain potassium-40. So that process of potassium-40, for example, turning into argon is known as radioactive decay. The potassium-40 is decaying into argon. So it's the transformation of an unstable isotope, like potassium-40, into a lighter one, like argon. And radiation is released in the form of particles. So we have this concept in radiometric dating. The concept is half-life. And this is the time it takes for 1/2 of a radioactive isotope to decay. 1/2 of any amount of any radioactive isotope to decay. So picture in your mind a volcano. And the volcano is erupting, and lava is being spewed from the volcano. Think of Hawaii, right? And that's what built the Hawaiian Islands, and it's still going on. So the lava solidifies, and when it solidifies into rock, it has its maximum amount of potassium-40, right? It has a certain amount of potassium-40, and it really doesn't have much argon at all. And over time, that potassium-40 will turn into argon. And we can tell how long ago the lava solidified into rock by how much potassium-40 and argon we find in that rock. So when half the potassium-40 is gone, the period of time it took for that to happen, for half of the potassium-40 to go away, not go away, but to decay into argon, that's known as its half-life. And if you look on the scale here, we're talking billions of years. So for any sample or amount of potassium-40, it takes about 1.2 billion years for half of it to turn into argon, to radioactively decay into argon. It takes another 1.2 billion years, approximately, for another half of it to decay. So every 1.2 billion years, another half has decayed into argon. That's half-life. So radiometric dating measures absolute age by determining how many half-lives have passed. How many half-lives? So if one half-life has passed, that's 1.2 billion years. If 2 half-lives have passed, it's 2.4 billion years, or 2.5. It's actually not exactly 1.2 billion years, the half-life. But hopefully you get the idea. We just need to determine how many half-lives have passed, and we can do that by measuring the proportion of potassium-40 versus argon in a rock. So in this example, radiometric dating is performed by determining the relative proportion of potassium-40 versus argon, like I just said. Argon is its decay product. And if you don't understand it here, hopefully you will after performing the gizmo that is assigned this week along with this information. So we find the number of past half-lives to determine the absolute age. So there are different radioactive isotopes that can be used to do this, and potassium-40 is a good one if you know that the rock or the fossil is really, really old, because its half-life is on the scale of billions of years. There are other radioactive isotopes that have shorter half-lives. So our solar system and the Earth is about 5 billion years old. So potassium-40 is a good one to use if you want to measure the age of a rock, some of the oldest rocks on Earth, or even rocks that, like a sample from an asteroid or the moon. If you want to find out how old those rocks are, potassium-40 would be a good one, because its half-life is on the order of billions of years. Carbon-14 you may have heard of. One form of radiometric dating is carbon-14 dating, and notice that its half-life is only 5,700 years. So it's more appropriate for determining the age of a fossil that of an organism that died more recently. So, for example, archaeological digs, once living humans, mummies. Carbon-14 is really good for absolutely dating those kind of things. So they need to have died within the past 30,000 years or so, not billions of years like for argon-40. All right, so that brings us to the geologic time scale. And the geologic time, or the geologic time scale, is a system to measure and communicate about the huge amount of time that has passed since the Earth first formed, about 4.8 billion years ago, so almost 5 billion years ago. And it's divided up, and it'd be very useful to you to remember the hierarchical setup of the geologic time scale. And what we're seeing here are eras and periods, but there are eras divide up eons. So there's a geologic time period even greater than an era, known as an eon, and periods can be divided up into epochs. And you may have heard those terms before, eon, I'm sure you have, and epochs. So the order that would be good for you to remember these terms would be eon, era, period, epoch. Eon, era, period, epoch. If you can remember that, it will help a lot, especially in the explanation that you're about to get. So it's developed, the geologic time scale was developed by geologists, but it's primarily based on fossils. So, so I mentioned earlier that paleontology is a subdivision of biology. It's kind of also a subdivision of geology. So geology and biology together. I mean, if you're going to become a paleontologist, you've got to take a lot of both geology and biology. But so the time scale is based mostly on fossils. So how we know time has passed on the Earth is based on how we know life has changed on the planet. So an era is a subdivision of time that divides an eon into smaller units of time. So again, eons, eras divide up eons. The Precambrian is divided into the Hadean, Archean, and Proterozoic eons. We're not going to spend any time really with those eons at all, because they really don't, except for the Proterozoic. Not even the Proterozoic. So these eons don't involve life much at all. The Phanerozoic eon, however, does, and it follows the Precambrian and extends to the present. So the Precambrian spans from the formation of the Earth about 4.8 billion years ago. So that's what I'm trying to get across with this arrow. This arrow means think back 4.8 billion years ago. The time period we're looking at here is only 650 to 544 million years ago. What I need you to understand is that Precambrian time did not begin 650 million years ago. It extends all the way back 4.8 billion years to the beginning of the planet, the formation of Earth. It's called the Precambrian because it's the entire period of time before the Cambrian period, which we don't even see on this slide. It's after the Vendian. We see the Vendian period here. The Cambrian period begins at 544 million years ago. So it's after the Vendian period, as we'll see on the next slide. So the percentage of the Earth's history that is Precambrian is about 80%. So most of the Earth, the time that the Earth has been in existence, was the time before 544 million years ago, and that's all known as the Precambrian, 80% of the Earth's history. Periods are subdivisions of eras, right? You can see that here from the diagram. Periods are subdivisions of eras. The Vendian period is designated by the very oldest evidence of multicellular animal life. And this is known as the Ediacara fauna, because it was found in the Ediacara hills in Australia. So this time period is also known as the Ediacarian. So Vendian and Ediacarian periods are used interchangeably. The event that marks the end of the Precambrian or the Proterozoic eon or the Vendian period is the Cambrian explosion. And they call it the Cambrian explosion because there's this sudden appearance in the fossil record of animal life. But that's not to be confused with the Big Bang. The Cambrian explosion and the Big Bang are two completely different things. The Big Bang is the beginning of the existence of the universe, and that's about 15 billion years ago. The Cambrian explosion is the sudden appearance of animal life in the fossil record that happened about 544 million years ago. So don't confuse those two concepts. They're two completely different things. So here we go from the Precambrian era to the Paleozoic era. And again, Precambrian refers to before the Cambrian period. So here it is, the Cambrian period, beginning 544 million years ago after the Vendian period. So the three eras that make up the Phanerozoic eon, because remember the Paleozoic here is the beginning of the Phanerozoic eon. So the Phanerozoic eon is divided up into three eras. That's the Paleozoic, which we see here, the Mesozoic, which you probably are familiar with because that's when the dinosaurs were around, and the Cenozoic, which is ongoing right now. And the Paleozoic is divided up into these periods, and I'm just going to say them for you just so you can hear them pronounced here. So, of course, we got the Cambrian, the Ordovician, the Silurian, the Devonian, the Carboniferous, and the Permian periods. Paleozoic means ancient life. So whenever, there are a lot of parts of words here that end in zoic. Those are referring to life. Zoic, kind of referring to zoo or animal. So ancient life, Paleozoic. Just like a paleontologist studies ancient life. Paleo refers to ancient. The periods that I just read off for you are generally named for where fossils were discovered from that time. And by the end of the Paleozoic era, in other words, by the end of the Permian period, fish, amphibians, reptiles had evolved, as well as the lines of evolutionary descent that would lead to dinosaurs and birds and mammals and us. So a lot happened during the Paleozoic era in terms of setting the stage for the evolution of the life that we now have on the planet. The end of the Paleozoic era and the Permian period ended in the greatest mass extinction ever discovered. And we don't know exactly what happened, but it's also referred to as the Great Dying because a huge percentage of the Earth's life died at the end of the Permian period. And we'll be looking at that more specifically later on. The next era of the Phanerozoic eon is the Mesozoic era. And again, this is the one that you may be most familiar with because it is when the dinosaurs lived. So these periods probably are going to sound very familiar to you: the Triassic, the Jurassic, and the Cretaceous. Mesozoic means middle animals. Meso means middle, right? So Paleozoic is ancient animals. Mesozoic is middle animals because it's the middle era of the Phanerozoic eon. So the major terrestrial animal group, or class, because the class that includes reptiles is class Reptilia, are the reptiles, most notably the dinosaurs. The major event that marks the end of the Mesozoic era and Cretaceous period, so right here at about 65 million years ago, you know what happened. There was a second mass extinction event. So second to the Permian extinction that we were just looking at, or that I just mentioned on the previous slide. This one wasn't as big as the Permian extinction, but it was big enough to basically remove the dinosaurs from the game. Took them out. Finally, we have the Cenozoic era. So the Phanerozoic eon is divided into 3 parts, Cenozoic being the last era. Cenozoic means new animal. And the new animals that have that basically took over after the dinosaurs were removed are the mammals. So the class, which is also a class, so just like reptiles are class Reptilia, mammals are class Mammalia. And that brings us to the present. Now, there has been proposed an addition to the geologic time scale that involves evidence of human activity on the planet, and it's becoming widely accepted now as the next geologic time period, and that would be the Anthropocene. Just like anthropology is the study of humans, the Anthropocene refers to the period of time where future scientists may find, or even alien beings may find evidence of human activity on the planet, and that's what we're in right now, the Anthropocene. And just to pronounce these for you, and I'm sure you can read these for yourself, but Tertiary and Quaternary periods. This is a look at the entire geologic time scale. And so as you can see, it is divided up in many different ways. But again, here we have the eons and the eras and the periods. It just gives you a better idea of the whole picture, right? And the epochs that I mentioned. And you'll notice that some of the periods are divided up into early and mid, middle, and late. And the Cambrian is even divided up into letters of the alphabet, interestingly. So we're not going to get into it in this much detail, but I wanted you to get a better idea of the entire geologic time scale.